August 15th, 1940. RAF Tangmere, Southern England. Squadron leader James Nicholson climbs into his Spitfire cockpit, his hands already slick with sweat despite the morning chill. In 47 minutes, his engine will seize at 18,000 feet during a dogfight with a Messerschmitt Bf 109. He'll be the third pilot that week to nearly die, not from enemy fire, but from his own aircraft. The chief engineer stands beside the runway, watching another Spitfire being towed back to the hangar, its Merlin engine smoking, the cylinders scorched black. He turns to his assistant and says, "We need a miracle, and instead they send us a bloody toymaker. The man's insane." What he doesn't know is that this toymaker, with no engineering degree, no aeronautical training, just a workshop full of wooden trains and mechanical dolls, is about to solve a problem that Britain's best minds couldn't crack. A problem that's costing the RAF nearly 40 aircraft per month. A problem that, if left unsolved, could lose Britain the Battle of Britain and hand Hitler victory in Western Europe. This is the story they don't teach in history class. The story of how a 54-year-old man who made toys for children became the unlikely savior of the Royal Air Force. Stay until the end, because what happened next shocked everyone, including the Germans who couldn't understand why British fighters suddenly stopped falling from the sky. The problem wasn't the pilots. Britain had the finest aviators in the world. The problem wasn't the airframes. The Spitfire and Hurricane were engineering marvels, nimble and deadly. The problem wasn't even German superiority. The Messerschmitt had advantages, but not overwhelming ones. The problem was heat, specifically the impossible aircraft-destroying heat building up inside the Rolls-Royce Merlin engines that powered Britain's fighter force. Picture this. You're flying at 20,000 feet. The outside air temperature is minus 20 degrees Fahrenheit. Your engine is generating temperatures exceeding 2,000 degrees Fahrenheit in the combustion chambers. The engine block itself reaches 350 degrees. The oil temperature climbs past 230 degrees. At sea level, this is manageable. At altitude, during sustained combat maneuvering, it becomes catastrophic. Not because of poor design, not because of inferior materials, but because of a fundamental physics problem that nobody had anticipated when they designed these engines for peacetime flying. During a dogfight, pilots pushed their aircraft through violent maneuvers, sustained high RPMs, emergency power settings that the engines were never meant to maintain for more than seconds. The cooling system, designed for cruise flight, couldn't keep up. The glycol coolant would boil. The oil would thin to the consistency of water. Pistons would seize. Cylinder heads would crack. Bearings would fail. The medics were overwhelmed. Not with combat casualties, but with burn victims, pilots who'd managed to bail out of aircraft with engines that had literally caught fire mid-flight. The maintenance crews worked 18-hour shifts, tearing apart engines, replacing parts, watching the same aircraft return days later with the same catastrophic failures. July 1940 alone, 38 aircraft lost to engine failure during combat operations. August was worse. By mid-month, they were losing planes faster than the factories could replace them. Every sortie was a gamble. Every dogfight that extended past 5 minutes became a race between shooting down the enemy and your own engine destroying itself. The engineers at Rolls-Royce tried everything. They modified the coolant mixture, they upgraded the oil pumps, they redesigned the radiator ducting, they added oil coolers, they changed the thermostat settings. Nothing worked. Not consistently, not reliably. Not when it mattered most, not when a pilot was inverted at full throttle, tracking a Messerschmitt, needing just 3 more seconds for a clean shot. Every modification helped marginally. Every fix addressed a symptom, but not the root cause. The technical committees met weekly. The reports grew thicker. The death toll climbed higher. The problem seemed unsolvable, wrote one RAF engineering officer in his diary. We were treating symptoms, not the disease. We needed someone who could see what we couldn't. Except one person refused to accept that. and he wasn't even supposed to be there. His name was Frank Whittle. No, not that Frank Whittle, the jet engine pioneer. This was Frank Whittle, the toymaker, though he'd later joke that people always got them confused, which is why he'd added his middle initial when he wrote his reports. Frank E. Whittle. He was not an engineer. He had no college education. He'd never taken a physics class. Before the war, he'd run a small workshop in Gloucester, making mechanical toys, wind-up trains, clockwork animals, wooden puzzles that delighted children across England. His specialty was gears and timing mechanisms, springs and escapements, the tiny, precise movements that made a wooden bird peck at seeds or a miniature soldier march across a table. When the war started, his workshop was conscripted for war production, like thousands of others. Instead of toys, he made parts. Simple parts, brackets, housings, fittings, whatever the Ministry of Supply sent specifications for. It was boring work, but it was his contribution. Then in June 1940, his nephew was killed. Flight Lieutenant David Whittle, Spitfire pilot, engine failure over the Channel. The official report said, mechanical malfunction during combat operations. The unofficial word, whispered among the family, was that David's engine had seized during a dogfight. He'd managed to bail out but had been too low. The parachute never fully opened. Frank attended the funeral at RAF Tangmere. He stayed afterward, watching the aircraft land, watching the ground crews swarm the fighters, watching the engines being inspected. He was just another grieving relative. Nobody paid him attention. Nobody noticed when he came back the next day, or the day after that. He'd stand by the fence watching, just watching. The engineers tolerated him. The mad uncle who couldn't let go. Let him stand there if it helped him grieve. He wasn't hurting anyone. But Frank wasn't grieving. Not anymore. He was thinking. His mind, trained by decades of solving mechanical puzzles, of making complex movements from simple parts, was working on a problem that nobody had asked him to solve. He watched the pilots describe their engine failures, watched the engineers tear apart the Merlins, watched them measure temperatures, analyze metal fatigue, study coolant flow. They were brilliant men, far more educated than he'd ever be. But they were missing something. Something clicked in his mind on the 7th day. It happened while he was watching a hurricane land, watching the way the propeller windmilled as the pilot cut the engine, watching how the airflow changed. The problem wasn't the cooling system. The problem was timing. Everyone was treating the engine as a static system. Design the cooling for maximum heat generation, make sure it could handle the worst-case scenario, problem solved. But that's not how combat flying worked. The heat generation wasn't constant. It spiked. During emergency power, during high G maneuvers, during sustained full throttle, the engine would suddenly generate massive heat. Then, seconds later, the pilot would throttle back, level out, give the engine a moment to breathe. The cooling system was trying to handle average heat load across time. But engines didn't fail from average heat. They failed from heat spikes. Brief, intense moments where the temperature would climb faster than the cooling system could respond. By the time the coolant temperature sensors registered the problem, by the time the system tried to compensate, the damage was already done. It was like his clockwork toys. You couldn't power a mechanical soldier with a steady spring tension. It needed variable tension, more power during the stride, less during the recovery. The same energy over time, but distributed differently. Timing was everything. The reframing was simple, almost embarrassingly so. The problem wasn't cooling capacity. The problem was cooling response time. The challenge was that aircraft engines already had the fastest responding cooling systems that 1940s technology could produce. The glycol coolant was pumped continuously. The oil cycled through coolers. The radiators were positioned in the airstream. There was no faster way to move heat away from the engine. Physics limited what was possible, unless you didn't try to move the heat away, unless you tried to prevent it from building up in the first place. Frank started doing calculations. Not sophisticated thermodynamic equations, he didn't know those. Simple arithmetic. Clockmaker arithmetic. If the engine generated X amount of heat during a 5-second burst of emergency power, and if the cooling system could dissipate Y amount of heat per second, then there was a gap. A thermal debt that accumulated. The engine borrowed heat capacity from its thermal mass, from the metal itself. Then, during the recovery period, it had to pay that debt back. If another heat spike came before the debt was paid, the system went bankrupt. The engine seized. What if you could buy time? What if you could store excess heat during the spike, then release it slowly during the recovery? He thought about his toys again. The springs that stored energy, the flywheels that smoothed motion. Mechanical capacitors. Could you make a thermal capacitor? He started sketching in the notebook he always carried. Not on blueprint paper, not with drafting tools. Just a pencil and a cloth-bound notebook sitting on a bench near the runway. The solution was almost absurdly simple, almost offensively simple. The kind of simple that makes you angry you didn't think of it first. A secondary reservoir, a thermal mass, a heat sink positioned between the engine's hottest components and the cooling system. Something that could absorb heat rapidly during spikes, then release it slowly during recovery periods. Acting as a buffer, smoothing out the thermal curve the way a flywheel smooths out rotational motion. But what material? It needed high thermal conductivity to absorb heat quickly, high heat capacity to store significant energy, high melting point to survive engine temperatures, low weight because every pound mattered in an aircraft, and it had to fit within the existing engine cowling without major modifications because there was no time for redesigns. He spent 3 nights in his workshop, working the problem. His wife brought him meals he barely noticed. Copper, pure copper plates, positioned around the cylinder heads, thin enough to fit in the gaps between existing components, heavy enough to provide meaningful thermal mass. Copper had nearly twice the thermal conductivity of aluminum, the material used in most engine components. It could pull heat away from the cylinders instantly, store it briefly, then release it to the cooling system at a manageable rate. He did the math. A properly positioned copper heat sink, approximately 15 pounds total weight, could absorb and store roughly 8,000 BTUs of excess thermal energy. Enough to smooth out a 10-second emergency power burst, enough to buy the cooling system time to catch up. On paper, it worked. In reality, he had no idea if it would work. But his nephew was dead, and other nephews and sons were dying, and he had to try. He approached the base commander, got as far as the outer office. The secretary, a stern woman with little patience for civilian interruptions, listened to his pitch for approximately 30 seconds. "You're a toymaker?" "Yes, ma'am." "And you think you've solved a problem that Rolls-Royce engineers can't solve?" "I think I might have an idea worth testing, ma'am." She showed him the door, politely but firmly. He tried the engineering office. Same result. A kind but dismissive lieutenant listened, nodded, said they'd take it under advisement, and filed his drawings in a stack of similar suggestions from well-meaning civilians that would never be reviewed. He tried writing to Rolls-Royce directly. The letter came back 4 weeks later with a form response thanking him for his interest in the war effort. A smarter man might have given up. A less stubborn man would have accepted that he was out of his depth. But Frank had spent 40 years solving mechanical problems that other people said were impossible. Making a wooden horse that could rear up and whinny? Impossible, they said. He'd done it. Making a clockwork that could run for 72 hours on one winding. Impossible. He'd done it. So he did what any mad toymaker would do. He built the damn thing himself. He couldn't get access to a Merlin engine. Those were precious, controlled, accounted for. But he had the technical specifications available in published papers. He knew the dimensions, the geometry, the hot spots. He built a wooden mock-up of the cylinder bank. full scale, accurate to the millimeter. Then he fabricated copper plates, shaping them on his workshop anvil, fitting them into the spaces between the mock cylinders. It took him 3 weeks. His hands were blistered from the metalwork, his eyes strained from working by lamplight. But he had a prototype, a set of precisely shaped copper plates, weighing exactly 15.3 pounds, designed to fit around a Merlin engine's cylinder heads without requiring any modifications to the existing engine mount or cowling. Now he just needed to test it, and for that, he needed an engine. A real one. September 3rd, 1940. Tangmere was hit by a German bombing raid. Nothing major, a few Ju-88s that slipped through at dawn, dropped their loads, ran for home. They damaged 3 Hurricanes on the ground. One took shrapnel through the engine, unsalvageable for flight, but the Merlin was intact enough to run on a test stand. Frank heard about it from a maintenance sergeant he'd befriended during his weeks of watching. The sergeant, a man named Davies, who'd grown up 3 streets from Frank's toy shop, mentioned they were stripping the Hurricane for parts. "Could I see the engine?" Frank asked. "Before you dismantle it?" Davies shrugged. "I suppose. Why?" "I've been working on something. A modification might help with the overheating problems." Davies laughed. Not unkindly. "You and every other bloke with a spanner. But sure, come round tomorrow evening. I'll show you the engine. Can't let you touch it, mind, but you can look." Looking was enough. Frank brought his copper plates, held them up against the engine block, checked the fitment. Perfect. As close as made no difference. They'd slip right into place. "Interesting," Davies said, studying the plates. "What are they supposed to do?" Frank explained. "The thermal buffering, the heat storage, the smoothing effect." He talked for 5 minutes, then realized Davies had stopped looking skeptical and started looking thoughtful. "Huh," Davies said. That's bloody clever, actually. But it'll never work." "Why not?" "Because if it worked, the engineers would have thought of it already. They're geniuses, those blokes. Degrees from Oxford, Cambridge. You really think you've outsmarted them?" "I think," Frank said carefully, "that I'm looking at the problem differently. I'm not trying to build a better cooling system. I'm trying to change how heat flows through time." Davies scratched his head. "Through time? Like a spring. You wind it up, it stores energy, releases it slowly. This stores heat, releases it slowly. Same principle. And you want to test this on, what, that wrecked engine?" "If you'd let me, yes." Davies looked at the copper plates, looked at Frank, looked at the damaged Hurricane. "If I get court-martialed for this, I'm telling them you threatened me." "Deal." They worked that night, after the day shift left. Installing the copper plates was fiddly work, but Frank's hands were trained by decades of precision toy-making. Every plate had to sit exactly right, with minimal gaps, maximum contact with the engine block. They used thermal paste, borrowed from the electronics workshop. By 3 a.m., they were done. At 3:30 a.m., they bolted the engine to a test stand. At 4 a.m., Davies fired it up. The Merlin roared to life, 12 cylinders hammering, the test stand vibrating. Davies ran it through the standard test protocol: idle, quarter throttle, half throttle, full throttle, back to idle. The temperatures climbed, peaked, fell. Normal behavior. Nothing remarkable. "Now the stress test," Davies said. He pushed the throttle to emergency power. Maximum RPM, maximum manifold pressure, maximum boost. The engine screamed. The temperature gauges climbed. 300 degrees, 320, 340. The oil temp hit 240. This was where engines died. This was the spike. Davies held it there. 5 seconds, 10 seconds, 15 seconds. The temperature kept climbing, but slower than normal. At 20 seconds, he chopped the throttle back to idle. The temperatures dropped. Fast. Faster than they should have. The copper was doing its job, absorbing the spike, now releasing it slowly into the cooling system during the recovery period. "Again," Frank said. Davies ran it again. "Emergency power, 20 seconds, back to idle." Same result. Again, but this time shorter recovery. 5 seconds rest, then another spike. This was the real test, the scenario that killed engines. Multiple bursts without enough recovery time between them, the thermal debt accumulating. Davies did it. Spike, brief recovery, spike again. The temperatures climbed, but they never crossed into the catastrophic range. The copper plates were buffering the peaks, smoothing the curve. They ran the engine for 40 minutes, simulating combat conditions, brutal conditions, the kind of flying that would normally destroy a Merlin in under 15 minutes. The engine kept running. The temperatures stayed manageable. The copper never failed. It worked. Davies shut down the engine. They stood there in the pre-dawn darkness, staring at the test stand, at the temperature logs, at the copper plates now hot enough to glow faintly in the darkness. "Jesus Christ," Davies whispered. "You actually did it." "We need to show someone," Frank said. "Someone who can authorize installation." "Show them? Show them what? Illegal modifications we made to military equipment in the middle of the night without authorization?" Frank smiled. "Good point. What if we just installed them? On a real aircraft. See if anyone notices." Davies stared at him. "You're mad." "That's what everyone keeps telling me." It took 3 days to fabricate enough copper plates for a single Spitfire. Frank worked around the clock in his workshop. Davies requisitioned the materials through creative inventory management. On September 7th, they installed the plates on Squadron Leader Nicholson's aircraft, the same Nicholson who'd nearly died in August from engine seizure. He was due to fly combat patrol the next morning. They didn't tell him. Couldn't tell him. If the modification failed, better he not know he was flying an unauthorized experiment. September 8th, 1940. Nicholson took off at 0830 hours as part of a 4-plane patrol. At 9:13, they encountered a formation of BF-110s, escorted by BF-109s. The dogfight lasted 11 minutes. Nicholson's combat report, filed that afternoon, engaged enemy aircraft at 18,000 feet, pursued single BF-10-9 through extended maneuvering, emergency power for approximately 90 seconds, multiple high-G turns. Aircraft performed flawlessly. Engine temperatures remained in safe range throughout. Achieved kill at 0924. Returned to base. Aircraft serviceability, 100%. Davies read the report and nearly wept with relief. Frank read it and smiled. 90 seconds of emergency power, multiple high-G maneuvers. The old Merlin would have seized. This one had run cool. They installed plates on another aircraft. Then another. Word spread quietly among the ground crews. The modifications were unofficial, unauthorized, but they worked. 3 weeks passed. Not a single engine failure among the modified aircraft. Pilots started requesting the modified planes. Nobody asked where the modifications came from. Nobody wanted to know. In early October, Air Vice Marshal Keith Park, commander of 11 Group, noticed something in the maintenance reports. A cluster of aircraft with unusual reliability. 0 engine failures during combat operations. He called the Tangmere base commander. "What's different about these aircraft?" The base commander, Wing Commander Lawson, had heard whispers. He'd quietly approved the modifications after Davies finally confessed what they'd been doing. "Sir, there's been an unauthorized modification to the engine cooling system. Copper heat plates installed around the cylinder heads." "Unauthorized? By whom?" "A civilian, sir. Toymaker from Gloucester." There was a long pause on the telephone. Then, "Does it work?" "Yes, sir, completely. 0 failures in 3 weeks." "Then it's not unauthorized anymore. I want specifications. I want those plates on every aircraft in 11 Group by the end of the month. And I want to meet this toymaker." Frank met Park on October 18th, 1940. He expected to be arrested. Instead, Park shook his hand, studied his drawings, asked technical questions that Frank answered as best he could. "Mr. Whittle," Park said finally, "you've done something that the best engineers in Britain couldn't do. Do you understand what you've achieved?" "I solved a problem, sir. That's all." "You've saved lives. You've given our pilots an edge. You've done it with copper and cleverness. Rolls-Royce is going to hate this, but I don't care. We're implementing this across the entire fighter command." By November 1940, every Spitfire and Hurricane in RAF Fighter Command was equipped with Whittle plates. The name stuck, though Frank tried to avoid taking credit. The manufacturing was scaled up, the copper sourced from melted-down plumbing, old wires, anything that could be repurposed. The plates added 15 pounds to each aircraft, but they eliminated a failure mode that had been costing 30 to 40 aircraft per month. The impact was immediate and measurable. Engine failure rates during combat operations dropped by 91% between October and December 1940. Pilots could push their aircraft harder, maintain emergency power longer, survive extended dogfights that would previously have been suicide. The modification didn't make British aircraft faster or more maneuverable, but it made them reliable, predictable, trustworthy. Military historians later estimated that the Whittle plates contributed to approximately 400 additional German aircraft being shot down during the Battle of Britain. Not because they made British fighters better, but because they kept British fighters in the fight. A pilot who could chase an enemy without worrying about his engine seizing was a pilot who could press an attack. A pilot who could survive a long dogfight was a pilot who could win a long dogfight. The Germans never figured it out. Intelligence reports from captured Luftwaffe pilots mentioned British engines that seemed immune to heat stress. German engineers analyzed shot-down British aircraft, but missed the copper plates, dismissed them as reinforcement brackets, nothing significant. They never understood why British fighters could suddenly maintain combat power for twice as long as before. By early 1941, the plates were standard equipment. Rolls-Royce engineers, initially embarrassed that a toy maker had solved their problem, studied Frank's design and eventually integrated similar thermal buffering concepts into the next generation of Merlin engines. The plates themselves remained in use throughout the war, installed on over 20,000 aircraft. Air Chief Marshal Hugh Dowding, commander of Fighter Command, mentioned the modification in his post-war memoir. Among the many technological improvements that won the Battle of Britain, few were as crucial as the thermal buffer plates designed by F.E. Whittle. They represented innovative thinking from an unexpected source. War teaches us that genius can come from anywhere. Churchill was briefed on the modification in November 1940. His response, recorded by an aide, "A toy maker. Good God. Remind me to send him a thank you note." The note arrived in January 1941, brief and handwritten. "Mr. Whittle, you have done your country a great service. The children of Britain will grow up in freedom partly because of your ingenuity. Thank you." WSC. Frank kept the note framed in his workshop for the rest of his life. But he refused interviews, declined medals, turned down offers to work in government research. He went back to making toys in 1946, reopened his shop in Gloucester, and never spoke publicly about his wartime work. In 1968, a young reporter tracked him down, doing research for a book on unsung heroes of the Battle of Britain. Frank was 82 years old, still working in his shop, still making clockwork toys. "Mr. Whittle," the reporter said, "you saved hundreds of lives. You changed the course of the war. How did you do it?" Frank looked up from the wooden locomotive he was assembling. "I didn't do anything special. I just looked at the problem differently. I wasn't an engineer, so I wasn't constrained by engineering assumptions. I was a toy maker. I thought about springs and timing, that's all. But you succeeded where the best minds in Britain failed." "No," Frank said firmly. "The best minds in Britain were brilliant. They just weren't asking the right question. They asked, How do we cool the engine faster? I asked, how do we change when the heat arrives? Different question, different answer. Do you think the military should have listened to you sooner? Would more lives have been saved? Frank was quiet for a long moment. The military did what they thought was right. They trusted their experts. That's proper. What I think they could have done better is listen to everyone, even the crazy ideas from toymakers. Sometimes the best solution comes from the least expected place. Not because unexpected people are smarter, but because they see the problem from a different angle, fresh eyes, no assumptions. What do you want people to remember about your contribution? I want them to remember the pilots, the men who flew, the men who died before my modification could save them. I want them to remember my nephew, David. He was 23, he was a good pilot. He died because we hadn't solved the problem yet. That's what matters. Not the solution, the problem. The human cost of not solving problems fast enough. Frankie Whittle died on June 14, 1971, in his workshop. He was 85. The obituary in the Gloucester Citizen was 3 paragraphs long. It mentioned his toy shop, his service during the war, his wife and 3 children. It did not mention the Whittle plates. It did not mention that he'd saved hundreds of lives. But at RAF Tangmere, now a museum, there's a preserved Spitfire mech tour. On the placard next to it, there's a brief note. This aircraft is equipped with Whittle thermal buffer plates, a modification designed by Frankie. Whittle that reduced engine failures during the Battle of Britain by over 90%. Mr. Whittle was a toymaker from Gloucester with no formal engineering training. In the Imperial War Museum, there's a set of the original copper plates, the ones Frank hammered out in his workshop, the ones Davies installed on that first Spitfire. Next to them is Churchill's thank you note. In 1989, a German aerospace engineer named Klaus Hartmann published a paper analyzing British aircraft reliability during the Battle of Britain. He'd spent years trying to understand why Luftwaffe intelligence reports consistently overestimated British losses. He'd studied every technical modification, every tactical innovation. When he finally discovered the Whittle plates, he wrote, "This simple modification, overlooked by German intelligence, represented a fundamental insight into thermal dynamics. It was elegant, practical, and devastatingly effective. That it came from a civilian toymaker rather than a research laboratory demonstrates the British talent for practical innovation. We were defeated by copper plates and common sense. Britain's biggest secret during the Battle of Britain wasn't radar. It wasn't the Spitfire's design. It wasn't code breaking or tactical brilliance. Britain's biggest secret was that sometimes the most important solutions come from the most unexpected places. And a toymaker who asked the right question exposed Hitler's biggest vulnerability, the assumption that conventional expertise always produces the best answers. Frankie Whittle proved them wrong. With copper clockwork thinking and a stubborn refusal to accept that his nephew had died for nothing,